Hi there. Welcome back to the ComSci 201 lecture series. We are at our fourth session and we're still talking about propositional logic, but this time we'll be dealing with semantics. So under semantics, we'll be talking about semantic rules of different connectives, how to create truth tables, and some properties of sentences. So what is semantics? Semantics is just the meaning of a sentence or a set of propositions. It deals with truthfulness or truth value of a sentence or propositional expression. So what about interpretation? An interpretation is an assignment of truth values to each propositional symbol. So to learn more about it, we will be having examples later. So how do we create truth tables? Before we do that, we have to define what a truth table is. So truth tables are used to determine the truth value of a proposition or sentence for any given interpretation. How do you get the number of rows of a certain table? You'll just have to get the number of variables of the expression and then you use it as a power of 2. So the number of rows is equal to 2 raised to the number of variables. So for this example, P, just P has a truth table of 2 rows because it's just one variable, and 2 raised to 1 is 2. What about P and Q? P and Q has 2 variables, so 2 raised to 2 is 4. That's why the truth table for P and Q is 4. So here are some examples. Actually, these examples are semantic rules of each connective. So how do we create truth tables for each connective? First is the negation connective, or the not. Not P has one variable, right? So if the variable number is 1, then the number of rows is, correct, 2. 2 raised to 1 is 2. So how do we construct the truth table? First, we get the base form of the variable, which is P. And since there is one column for the variable, we will divide the number of rows, which is 2, into 2. So we will cut it into half. The first half should be all true, and the second half should be all false. So half of 2 is 1, so the first row is true, and the second row is false. Now we will evaluate the truth value of not P for each row. So for row number 1, where P is true, not P is false. For the value false, or P is false, not P will be true. So as you can see, a negation or a not just assigns the opposite truth value for the base variable. So if P is true, then not P is false. If P is false, then not P is true. Okay, now we go to P and Q. This is a bit trickier, but if you get the hang of it, it'll be very easy to construct the truth table. So for P and Q, there are 2 variables, so that's 2 raised to 2, 4. So we have 4 rows. First step, we create the first column, which is the first variable, the base form of the first variable, which is P. And we put here, we cut it into half. The first half should be true, true. The second half will be false, false. Now, for the next column, for the next variable, we will cut into half the first half of the first column, which is this half. So this half contains 2 rows. That is why for the second column, it will have true for the first half, the first row, and false for the second half of the second column. Now we do the same in the second half of the first column. So since it has all false, false, for that, we will cut it into 2 again and fill the first half with true and the second half with false. So this is true, true, false, false. The second column is true, false, true, false. Now let's evaluate P and Q. So P and Q is what? For P equals true and Q equals true, then P and Q is true. For P equals true and Q equals false, P and Q is false. For P equals false, Q equals true, P and Q equals false. And for P equals false and Q equals false, P and Q equals false. So what pattern can you see here? If both propositions are true, then P and Q is true. But if either of the propositions are false, then P and Q are false. It's like promising something to someone. I promise to give you an apple, and Q, I promise to give you an orange. So when I return to you and I give you just an apple, was I faithful to my promise? No, because I promised you both an apple and an orange. So just so that it'll be easy for you to understand, you remember this example. So I have to fulfill both promises so that my promise is true. What about this, P or Q? P or Q can be constructed the same way. Since there are two variables, we create 4 rows, and for the first column, that'll be TTFF, and for the second column, TFTF. So as you can see, the combination here dictates that if both P and Q are false, then that's the only time that P or Q will be false. So imagine this example. I promise to give you an apple or an orange or both. So that's the equivalent. So if I get back to you and I give you an apple, then I fulfilled my promise, right? So that's true. If I give you an orange, then I fulfilled my promise. That's also a true. If I give you both, so true, true, then I also fulfilled my promise. That's also a true. But if I get back to you and I gave you nothing, then that means that I lied to you. So that's why it's a false. I'm not saying that it's the direct example for that, but I use it to remind myself of how to deal with or how to treat or, how to evaluate or, and how to evaluate an and. So and, the rule is both should be true so that P and Q will be true. The rest of the combinations are all false. For P or Q, both P and Q should be false so that P or Q is also false. All of the other combinations will yield true. How about implication? So for implication, since there are also two variables, we will have 4 rows and the following columns. So for this connective, as you can see, the only time that it will become false is that if P is true and Q is false. So if the premise is true and the consequence is false, then P implies Q is false. So here's an example so that it'll be easy for you to understand. If it will rain, then I will jump off the cliff. So P is it will rain, Q is I will jump off the cliff. So look at the first combination. What if it rained and I jumped off the cliff? Then what I said was true, right? What if it rained and I did not jump off the cliff? Then that means that I was lying because I said that if it will rain, I will jump off the cliff, right? So what about this, FT? What if it did not rain? Actually, if it did not rain, then you will not care if I jumped off the cliff or not, right? Because the premise did not happen in the first place. So in that case, I did not lie. That's why both conditions are true. So that's the only example that I try to give myself whenever I forget the rule for implication. But if you're more systematic, then you will just have to memorize that an implication will yield false if the premise is true and the consequence is false. What about if and only if? So the rule here is that if both P and Q have the same value, then P if and only if Q is true. Otherwise, it's false. So here, as you can see, for the combination where P and Q are both true and both false, P if and only if Q is also true. But for the other combinations like TF or true false and false true, P if and only if Q is false. So let's look at this example so that you can appreciate what interpretation really means. So let's pause for a while and not think about the truth tables. So let's try to evaluate the sentence F, which is P and not Q, implies R, or Q if and only if R. So here's the interpretation. Again, we talked about interpretation being the assignment of truth values to each variable. So here's the assignment. P equals true, Q equals false, and R equals false. So how do we evaluate this expression? First, we will try to substitute each variable with a truth value. So here in this first line, we substituted all variables with true and false. So here we can say that true and not false implies false or false if and only if false. Now we will try to evaluate the innermost value or the connective with the highest priority, which is not F. So after evaluating not F, we will see that it's now true. And now we will try to look for the next highest priority connective, which is AND. So let's evaluate true and true. That is true, right? So now true implies false or false if and only if false. Now let's look for the next highest priority. According to the precedence rule, it should be OR, but since this implication is inside the parenthesis, then we will prioritize it. So true implies false is false. We remember that the only time that an implication becomes false is that if the premise is true and the consequence is false, so it's false. So now we rewrite the expression as false or false if and only if false. Now we will try to evaluate this disjunction. We said that the only time that a disjunction or an OR evaluates to a false is that when both variables or all variables are false. Since both variables are false, then false or false is false. We now rewrite it as false if and only if false. And as we recall, the only time that an equivalence or an if and only if becomes true is when both values are the same. Based on the rule, false if and only if false is true because both values are the same. So this whole statement here is true based on the interpretation where P is equal to true, Q is equal to false, and R is equal to false. So now let's talk about properties of sentences. A sentence can be satisfiable or a contingency if there is at least one interpretation that is true and at least one interpretation that is false. So it means that some interpretations will yield true and some interpretations will yield false. What about contradictory or absurdity? So a contradictory or an absurd sentence is false for every interpretation. How about a valid sentence or a tautology? A tautology is true for every interpretation. So later on in the examples, you will be able to understand this more. So here are some examples. P and Q. P and Q is obviously a contingency. Why? Because a while ago, let me go back, we looked at the truth table for P and Q. There are some interpretations. In the first row, this interpretation yields to true. The second row yields to false. So there are some interpretations that yielded to true and some interpretations that yielded to false. So P and Q is a contingency. So what about P and F? So we remember that the rule for a conjunction or an and is that both propositions should be true for it to be true. Since one of them is already false, then it will yield to all combinations of this will be false. Hence, this is a contradiction, or this is also called an absurdity. What about P or true? Again, if we try to remember, the rule for a disjunction or an or is that the only time it will be false is that if both propositions are false. Since one of them is already true, then any combination or any value assigned to P will yield to true. So this is a tautology. This sentence is valid. Okay, what about this? Let's try a complex example. So here we will be required to create a truth table so that we will determine if it's a contingency, an absurdity, or a tautology. So let F, this is a script capital letter, so that this is a sentence. Let F be equivalent to P implies Q and not Q, if and only if not P or Q. So how many variables do we have? We have 2 variables. So how many rows should we have for our truth table? 2 raised to 2 is 4. So let's form our table. Now I will be editing it so that we will answer it together. I hope you can still see the slide as I edit it. So as you can see, I tried to group each statement and assign a sentence for each substatement. That is so that I won't have to make the columns too wide. For example, P implies Q, I represented it with the script G. P or Q, I did not represent it because it's just short. But for not P or Q, I represented it with M. For P implies Q and not Q, I represented it with H. So I used G here to represent P implies Q. It's up to you how you want to use scripts. You can actually put all of these variables here if you want to, but for convenience sake, I just replace them with scripts. So how do we fill this table? For the first column, we will have how many rows again? 4 rows. So for the first half of the 4 rows, which is the first 2 rows, we will put T. And for the next half, we will put F. Now we divide, for the second column, which is Q, we divide the first 2 T's into 2, and we put T here and F here. For the next half, we also put T here and F here. So those are the combinations. Now let's try to evaluate not Q. So for Q equals true, not Q is false, and so on. I know that you can evaluate it yourself now. Now, what about P implies Q? So for P implies Q, we just need to know where P is true and Q is false. So that's the second row. So for this row, G is false, which is P implies Q. For the rest of the combinations, we evaluate them as true. What about this next sentence? G, or P implies Q, and not Q. So as we can see here, this is the column for G, and this is the column for not Q. Now the rule for AND is that both propositions or sentences should be true, so that it will be true. So which of these combinations has both true? Here it is. So the last row should be true. The rest is false. Now we go to P or Q. P or Q has a rule that if both of the propositions are false, then P or Q is false. So let's look at these two columns. Which of these have both propositions assigned false? The last row. So the last row will be false. Oops. The last row will be false for P or Q. The rest will be true. Okay, we're almost there. What about M? M is the negation of the previous column, which is P or Q. So the negation of P or Q is, if it's true, then this is false, this is false, this is false, and this is true. So it's just the negation of the previous column. And finally, we go to the whole function, or the whole expression, which is H if and only if M. So let's look at this column and this column. So we only look for the combination where both columns have true or both columns have false. So for this row, H is false, M is false, then H if and only if M is true, because both have the same value. FF is also true, FF is also true, and T, or truth is also true. So now, as we can see, all of the rows, or all of the interpretations, this interpretation, this interpretation, this interpretation, and this interpretation, all yield to a true. So what is this sentence? Right, it is a tautology. So let's look at the SAQs. This might be the last time that I'll be talking about the SAQs, unless we will encounter more corrections in the future. So here's the first example. F, which is P or Q and not P or Q. G is assigned to P or Q and P or not Q or not P. Finally, H is assigned to P or Q and not P or not Q and P. So let's look at the first example. We don't need a truth table to prove it. It's already an absurdity. It's a contradictory sentence. Why? Because it's a conjunction of P or Q and its negation. So if that's the case, and the rule for a conjunction or an AND is that both should be true, then it's impossible for both statements to be true, because if P or Q is true, then not P or Q is false, and vice versa. So this is automatically an absurdity. So now let's go to the second example. G is equal to P or Q and P or not Q or not P. As you can see, this is a correction in the ASAQ, because in the ASAQ it's stated as AND, but please correct that, it's an OR. Okay, so how do we create a truth table? We have two variables, so we have 4 rows. And for the first column, for P, we will put true, and true for the first half, and false, false for the second half, right? What about Q? So we divide this half into 2 again and put true, false, and this half into 2 again, so we put true, false. Now, what is the negation of P? We just get the opposite, false, false, true, true. The opposite of Q is false, true, false, true. Let's look at the first grouping. So F is derived from P or Q here. So P or Q is this. Where are they both false? In the last row. So it's only the last row that will have false, the rest will be true. For H, which is actually this part, we will consider this column and this column. So in these combinations, which are both false, we can see that the third row are both false, so that's where it will be false. The rest will be true. So M is actually F and H, so the conjunction of these two. So the since it's a conjunction, then both should be true. Since this is both true, this is also true. If this is both true, then this is true. Okay, now true and false is false. False and true is false. Finally, we try to get the value of this or not P. So we look at the column not P and this column. So let's see which combination has both false. The first column, the first row is false true. The second is false true. The third is true false. The fourth is true false. So all are actually true. So we can conclude that this is a tautology or a valid sentence. Now let's look at the last example. The last example is actually not grouped yet. So we can see P or Q and not P, or not Q and P. Here we will apply the precedence rule. Remember last time we talked about the precedence rule. So let's look for a not first. So we group the not first to itself. I don't have to put parentheses anymore. So not P and not Q will be evaluated first, and then let's look for an end. So we saw an end here, so let's group not Q and P together. We can see another end here, Q and not P, let's group them together. And then the next connective in the hierarchy is an or, so from left to right, let's group P or Q and not P together. And then the next one would be this or. So let's group this or, and then let's group this together. So that's the final grouping. Now we will create a truth table. There are 2 variables, so there will be 4 rows. The first column will have true, true, false, false again, and true, false, true, false. The negation of P is false, false, true, true. The negation of Q is false, true, false, true. So let's look at the first sentence, Q and not P. Q and not P. So here it is. So can you see here where they have both true? They are both true in the third row. So we will put true there and false in the rest of the rows. What about G? G is P or F. It's this first column here and or F. So in or, both should be false so that P or F is false. So this one is this row, or yeah, this row is both false. The rest are a combination. So this is false. The rest are true. What about M? M is not Q and P. Not Q here and P. So the rule is both should be true. Is there a combination where both are true? True, false, true, true, false, 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 true. So the second row is true. The rest are false. And finally, G or M. So this is G and this is M. So again, the rule for or is that both should be false so that it'll be false. So the last row is both false, so that'll be false. The rest is true. As you can see here, it's a mixture. Some of the final answers or final truth values are true and one of them is false. That means that it's not a tautology, it's not an absurdity. We call this a contingency. Okay, so we're done. Thank you for listening once again. Some announcements. The video for Module 2 will not be about everything in the second module. I want this to be released in time for your quiz, for the deadline of your quiz, so I will just be focusing on the important parts. So see you once again next time or next session. Have a great day. Bye.